And then we're going to start off where we left off yesterday on that chapter 27. I did post the handout for that, and after today's session I will post the handout for the chapter 29 as well, because I know some people like having those. So, where we left off with this diagram of the weird shaped houses. Okay, we were talking about during heating and cooling system, the pressures are a little bit different because of the stack effect, it's called, of the airflow. Okay, cool air falls, hot air rises. So when we're in a heating season, during the winter months, okay, we're pulling cold air in through any crack or crevice at the bottom of the building. Okay, it's going to rise and it's going to attempt to push out at the top. So stack effect is the word that's going on here. And again, we're going to talk more about that in the pressures, but this is just a very great diagram of how it shows. Now in the cooling season, okay, our house is cooler, we hope, than the outdoor environment. So the hot air, the cold air falls as it cools off. Okay, the warm air falls, becomes cool, and falls to the bottom portion, okay, of the house. These are very minute pressures, but the cool air tries to escape from the bottom of the house, okay, and the warm air replaces it. And again, you can tell this by holding your hand over outlets, electrical outlets on some of the walls, hopefully just the exterior walls, but sometimes you can actually feel this happen in the interior walls as well. Okay, that's called building leakage. When we're designing an HVAC system, we have to take into account these warm and cold airs coming in and out of the building, because that's building leakage. Okay, it is a heat load. It adds sizing and BTUs requirements to our air conditioning and heating systems. Okay, we have to have makeup air. Okay, in some buildings, one area of the building may require localized exhaust, okay, because of poor air quality, while the other areas of a building remain relatively clean. For the dirtier areas, it may be more energy efficient to supply makeup air from clean air-conditioned spaces of the building rather than to bring outside air in and condition it. Now think about buildings where you've seen commercial buildings as well as residential buildings, like your houses. Okay, there's some areas of the building where we have some pretty heavy exhaust going on. Okay, for example, most bathrooms have exhaust fans. Okay, in some of the older houses they counted the window for that, but the reality is that in newer, more modern construction, the exhaust fans are a requirement in bathrooms. In kitchens, we have heavy exhaust fans sometimes. I talk about the McMansions quite a bit as I describe the design term, but we have in the early 2000s, we had a big building spree where everyone's house had to be bigger than the neighbors. Okay, and we started putting commercial kitchens into residential construction. Okay, these commercial kitchens pulled a lot of the air out of the house. You turned on an exhaust fan in one of these things, the entire house went into a negative pressure within like 4 minutes. People's fireplaces were venting backwards into the house, so they suddenly needed a lot of makeup air. Okay, so makeup air is when we bring in outdoor air or inside air from another area of the building. Stratification occurs in every house. That's what I was just showing you in those other pictures. It's a gradual rise in air temperature from floor to ceiling. It's natural convection due to temperature. Sufficient air movement prevents stratification. Okay, if you're standing in a room without any air movement whatsoever, the temperature near the ceiling is going to be much higher than the temperature near the floor. Okay, now, sometimes that's a good thing. Okay, high-ceilinged rooms used to be part of the building trends before we had a standard of air conditioning. You built your rooms extremely high ceiling. Well, when you were standing at floor level, the air was colder. Now, with the fact that our ceilings are lower, okay, that doesn't work as well. So we have to worry about the stratification. Okay, so when we're designing ductwork, when we're designing vents, we take a look at the average HVAC use in the area, and that's where we put our return and supply vents. Okay, the further south you go, the return vents are mostly on the ceilings, as well as the supplies, because of that stratification. We want to get the heat off the ceilings. The further north you go, a lot of times this is all on the floor. Again, we can create the air pattern for our normal situation. Okay, because we want the air to in the north, we want the cold air to stay at floor level, be sucked into the return, and we want it to mix with the warm air being blown out of the supply registers. Now, when you have a second floor, they may be in the ceiling, but we do also create the air patterns because of the fan speeds. I could create sufficient throw from those registers to fix the stratification problems. We have to worry about sun heat loads. Okay, we have radiant heat. Okay, it becomes trapped in glassed areas. It heats the outside surface of the building. So again, radiant heat. We really have to be concerned about radiant heat in any of our heat loads. Okay, it heats outside surface of the building, but in larger commercial buildings, it does not heat the outside surface all at one time. We worry about color. Dark colors absorb more heat than light colors. Okay, a black roof is going to absorb more heat than a light roof. Okay, a dark colored outside house, the wood colors, the dark brick is going to absorb more heat than if you have white siding or a yellow painted house. We worry about surface characteristics. Light reflecting surfaces don't absorb heat that easily. Okay, a lot of commercial buildings, you get up there on the roof, they've done a white membrane that is shiny. Okay, you might need sunglasses to get it on a hot sunny day. It's a light reflecting surface, light color, absorbs very little heat. Okay, we do this with window tinting sometimes. Okay, you can put a tint on a window where occupants can see out. It happens a lot in office buildings, but it is very, very shiny. Okay, and it bounces that light off, and it doesn't absorb heat. I don't know if anyone's ever watches the show Engineering Failures. Okay, they had a building, I think it was someplace in London, where they put it was an odd-shaped building. It wasn't a flat up-and-down building. And they put these light-reflecting surfaces on the windows, and it was bouncing the light back so seriously that you could actually cook eggs on the sidewalk in front of neighboring shops because the light reflecting was that strong coming off that building. So, again, all of these things come into play when we're talking heat loads. Any questions on this? Okay. Vapor barriers keep water vapor from passing through the walls. If you have done construction work or been around new construction, you remember that they put, you have your outside sheathing, then you have your insulation, and then they put a plastic vapor barrier over that insulation between the insulation and the indoor walls. It's usually just stapled on there.
Talking about like Tyvek?
What?
Talking about like Tyvek?
Yes. Well, that's on the outside of the house totally. I'm talking about the one that's on the inside, over the insulation.
Oh, okay.
Okay, the one they staple after they put the insulation up, and some of the insulation bats actually contain this. So you have your Tyvek on the outside, you can have that plastic on the inside. That plastic is more used in the northern environments than it is in the southern environments. But the vapor barrier can be aluminum foil, plastic sheeting, and again, Tyvek is a brand name for the outside vapor barrier. Okay, but it's installed on the warm side of the heated space. Okay, so it's on what I'm talking about on this one is the one that's on the inside. Okay, prevents vapor from building up between the insulation and the heated space. Again, I want you to think about that glass of cold water that I've used a couple times in discussion examples. You have a glass of ice water sitting on top of a counter, okay, in a warmer room. all of a sudden I can be building up water vapor. Okay, you have your sheetrock. My inside environment is warm, my outside environment is cool. If I let vapor into that area, I can actually start building up mold on behind that insulation and sheetrock. So we throw a piece of plastic in there, it serves as a vapor barrier. Because believe it or not, vapor and humidity gets through sheetrock. It's a permeable surface. Okay, heat sinks. Okay, warm body radiates heat rays. When rays strike the surface of same temperature, rays reflect back. Surface remains at the same temperature. When rays strike surfaces with lower temperature, the absorption of the radiant heat, or the rays, is absorbed into the colder surface. The surface acts as what we call a heat sink. Okay, most buildings are great heat sinks unless they're shiny material or light colors. The darker material, the better heat sink it is. So when we're talking heat insulation, we want to reduce heat conductivity. Okay, it helps maintain desired temperatures more economically. We use different types of insulation material. And again, there's way more on the list of now insulation materials than just on this list. But in older houses, you find what we call mineral wool. We use expanded mica. We use balsam wool. We use urethane. We use cork. Of course, we use fiberglass. I call it the evil pink stuff or the yellow stuff because it gets all over your skin and you itch for weeks. But you have so much insulation material now. We also have the spray-on foam insulation that's becoming more and more popular. And now, and over the last couple of years, I've also seen an increase in they're mixing insulation right into the concrete, right into the brick material that they're using to build foundations and stuff. So the insulation has changed over the years as well. What they're doing is everything is becoming tighter. Well, the tighter houses are great for energy efficiency, but they're not all that great for air quality. And that's where we're going to do more discussion after we talk about air distribution and pressures. So any questions on so far what we've gone over this morning? Okay, that is chapter 27. So that's the one that you guys are currently working on, homework assignments and stuff like that. So I am going to move to chapter 29. We're skipping 28 for the moment. Don't let it panic anyone. We'll be back to it. But it's just easy. It's better for everybody if I do it in this order. It makes more sense. So let's talk about air distribution. Okay? We've already talked a little bit about properties of air, so this is probably going to be a little bit of a quick review on that one. We want to talk about the different types of air circulation systems. We want to talk about ventilation requirements. What I mean by ventilation requirements is how much fresh air do I need to bring in? I mean, in all seriousness, would you ever want to be in a building that doesn't have any fresh air coming in whatsoever? Okay, I call them giant petri dishes. There are some buildings like that out there, but I don't know, wouldn't be the place I'd want to be. We want to identify the basic types of air duct systems. Okay, we want to explain the relationship between air distribution, duct sizing, and design. And again, we're starting to get out of the basics and we're starting to get into a little bit more design. So it's going to be extremely important if I say something that doesn't make sense to you, please ask the question. Okay, and if you don't want to do it here online, ask me the question afterwards in a discussion board or something like that. I do read all the discussion boards. Okay, explain the operation and servicing of what we call air curtains. Okay, air curtains is just a barrier to the outside environment. We use them a lot, and in some places you don't even realize we're using an air curtain, but we're using an air curtain. Okay, believe it or not, in the shop, for those of you who are around that, if you think about the shop, you have that big open face cooler. I call it the deli cooler or the meat case or one of those things. You have that big open face cooler that was on sort of facing the right side of the shop behind that's up against that multiple door cooler, the ones with the glass doors. The front of that is an air curtain. I think I did explain that to a couple people who were standing around out there. We use air curtains all the way through buildings and as well as in refrigeration. So we've already talked about, we have different properties that affect system design. We have the weight of the air. We have the manner in which air absorbs heat. We have air separates into layers. We know air obeys gas laws. As temperature rises, pressure rises. As temperature drops, pressure drops. There is a temperature-pressure relationship in air, which, by the way, is why we never use it to leak check in refrigeration systems. We always use nitrogen, okay, because nitrogen doesn't expand and contract. Temperatures and pressures don't change based on temperature. Density of air changes with temperature and relative humidity. Think back to the psychrometric chart. How heavy it is, how dense it is, changes with temperature and relative humidity. So again, this just basically shows this, okay? I have three basic columns here. I have dry air, 50% air, 100% relative humidity air. In other words, this is wet. The 100% is wet. The 50% is on an average day in the summer. Well, we hope in an indoor environment. And dry air has no moisture whatsoever. Sahara Desert. At 70 degrees, my density and my volume is there, 0.07, 13.47. Okay, as the humidity increases, my density changes and my volume changes. Okay, because it becomes more dense, can fit more into it. Okay, as we change air temperature, they don't even have measurements that for over 200 degrees for 50% and 100% because you can't achieve it. So again, this is a table of what we were looking at on the psychrometric chart. So we have different heat in air. This is comes down to enthalpy. Again, think about your psychrometric chart. Enthalpy contains sensible heat and latent heat. Sensible heat I can measure. Latent heat I can't measure, but it's heat or energy stored within moisture and air. Warm air can hold more moisture than cold air because of dew points. Eventually, cold air will get cold enough where the moisture just falls out of it in rain or condensation. Relative humidity compares the moisture level of air at a given temperature with its highest possible moisture level. Absolute humidity is the amount of moisture in the air. This all comes down to basically an evaporative cooling system. Okay, evaporative cooling, all we're doing is using the latent energy. Okay, this is used very heavily in what we call swamp coolers that are used out in the southwest where the humidity is so low that I can put a pan or a pad, blow air across it. It cools the air because the water evaporates off so fast. And again, when you talk in your air conditioning term, you'll have a little bit more talk about these swamp coolers. I think there's a little section on it. But it's evaporative cooling. If I put a pan of water, if I blow air across it, that temperature is going to drop because as we evaporate off, the vapor I'm evaporating off contains latent heat. Same principle that's used in the refrigeration cycle in the evaporator. I boil that refrigerant off, it absorbs energy, and the heat goes away with it, leaving the remaining surface cold. Well, we're doing that when we're talking evaporative cooling just because the water evaporates, boils off, and leaves the remaining surface cooler. Well, if I blow air across that cool surface, I'm now getting cool air wherever that space is. That's evaporative cooling. Your body uses evaporative cooling when you're sweating. Okay, that water, your sweat should be evaporating off your body if the temperatures are right, and it leaves you feeling cooler. That's what you're doing. Stratification, again, we talked about this, but this is very important. The diagram on the right, these ceiling diffusers, okay, are set up in a specific way and designed in a specific way, those 4 ceiling diffusers, to allow the cold air or the warm air, depending on season, to be mixed with the air coming out of the diffusers. So we solve that stratification. Moving air prevents stratification. Remember, stratification is that cold air sinks to the floor, hot air rises to the ceiling. Proper placement of the components is very important. We have to place thermostats and humidistats properly. We have to replace supply and return outlets. Okay, in case you can't see it, right there, if you look towards there's a wooden wall. I'm not sure I can do this. We'll try. Okay, there's a wooden wall over here, to the left-hand side of the diagram. If you follow the center of that wall directly up between those 2 corner diffusers, there's a return grill in the center. It's very tough to see in the drop ceiling, and I don't know if you can see my mouse pointer, but it's over it right now. Okay, so you have a return grill in the center of that ceiling. Okay, right next to the wood thing. While my 4 outside diffusers are blowing air sort of in a downward pattern, my return grill is sucking air back into the system sort of in the center of the room. We obviously aren't going to put it in the center of the woodwork because it messes up the woodwork. But the goal is to get it in the center of the room. We have to space things properly. So air circulation we use for warm air heating. We can use gravity. We'll talk about that in a minute. Okay, we can use intermittent forced air, and we can use continuous forced air. Gravity is not used that often anymore unless you have a wood stove or a pellet stove in the basement area. Okay, we used to just put our furnaces in the basement, put a big grill in the center of the house when they had the big open stairways, and we used to just okay, the heat will rise. That was the way it used to be. Okay, then we went to intermittent forced air, where we're using forced air and ductwork. We're using fans and blowers that move air around when it's needed. Continuous forced air is a little bit different. It's used in commercial buildings more often. When the building is occupied, I'm always moving air. And I'm turning on and off heat and cooling when it's needed, but I'm always moving air. Comes back to commercial refrigeration. I told you guys evaporator fans never stop in commercial refrigeration. Well, in continuous forced air, the blowers always run, used very heavily in large commercial buildings. Intermittent forced air, that's what you guys have in your houses most often, if you have forced air heating or cooling. A cubic foot of cooled air will not change room temperature as much as a cubic foot of heated air. That's due to the temperature difference. Temperature difference you're going to see referred to as delta T. It will have a delta sign, you know, the little Greek triangle, and it will have a T, capital T. Delta T is the temperature difference. That's the temperature difference either between the return air, that's the air being pulled back to the system, or the supply air, which is the air going out to the system. Okay, we have to circulate a much higher volume of cooled air than we do heated air. Now, I don't know if any of you folks live in a house that originally didn't have air conditioning. Very, very frequent in the Northeast and the northern part of the country. Okay, the heating systems had much smaller ductwork. If we add air conditioning to a system that was designed for heating, you cannot circulate enough air. We get a lot of coil freeze-ups and other problems that happen when you can't circulate enough air. So a lot of times just adding air conditioning, you add a coil to it, to the furnace, it doesn't necessarily solve the problem. It doesn't necessarily cool properly. So it's something to be very aware of if you're ever a technician who's being asked to add air conditioning to a furnace. Okay, you have to look at the overall design of the ductwork. So when we design ductwork and systems and HVAC systems, we are designing with cooling in mind because of the large amount of air we have to circulate. So again, that's why a lot in design I do talk more about the cooling side, because if I have enough ductwork If I have enough airflow for cooling, I will have absolutely enough ductwork for heating. Okay, I'll have enough space for air circulation. So a lot of times we talk about cooling more often than heating in design. So there's two methods we can use to vary the airflow between the cooling and the heating loads. The first is the 2-speed or variable speed blower. Okay, I can set 1 speed for cooling, 1 speed for heating. In fact, that's most often what we do. We use a variable speed blower with a high speed setting for cooling. Okay, it's usually a black wire. That seems to be the industry standard. We use a low speed for heating, the red wire. Again, industry standard. People don't mess it up. Okay, and we use a high speed for cooling, low speed for heating, or someplace in between. We also are starting to use what we call electronically communicated motors, ECMs. Okay, they vary automatically based on the pressures in the furnace and the ductwork. The other thing we use, which is less and less frequent these days in residential, very frequent in commercial, is called an adjustable pulley system with a belt. Okay, and again, when we get back into the building, we'll show you this, but it's basically a pulley. You have a pulley, you have a sheave on the motor that's adjustable. The belt connects the blower, and the further apart we pull the belt, okay, changes, or the sheave on the motor, it changes the speed of the belt and the driven blower wheel. Okay, so, and this shows it in your chapter of reading a little bit more. Any questions so far of what I've gone over? Okay. We need to talk about room airflow as well. Okay. Room air movement depends on the number and size of duct outlets and return inlets. Okay. So number and size of duct outlets and the returns that go along with it are really important for room air movement. Okay, the velocity, that's the speed of the air moving through the supply outlets. And again, if we look at this opened up attic, we see an air handler in the center. We have a return plenum with a single return. By the way, we're going to talk more about that. That's a really bad idea. Okay, and then we have a supply plenum, and the supply duct and branches all come off this supply plenum. Okay? And again, we have a curved piece of flex duct in the front right corner of this. Again, we're going to talk more about that when we talk about proper duct design. There's a few really bad ideas in the system. Okay? The primary air is the outlet velocity. Okay? And the throw. This makes a difference. The throw is how far away from the register in the room that air pattern is actually felt. That is also dependent on the outlet velocity of that primary air. That's the air coming out of the supply. So there's, again, two key factors, outlet velocity and throw, that control the primary air. And I think there's a homework question on that. The total air openings determines its capacity. Okay, so again, if I have a system with just one supply branch in every room, it has a lower capacity. If I have 2 or 3 in every room, it has a higher capacity. So we base this on the size of the rooms. So as we start talking about blueprints, it's going to become very important to be able to figure out how many supply branches you have to have in each room. Again, that's why I do this first before we go into blueprints. Airflow in a room has to be balanced. If I have more return air than supply air, it creates a negative pressure in the room. Okay, by negative pressure, I mean that the air pressure in the room is lower than the air pressure in the other rooms of the house or the outside environment. If I have a negative pressure in a room, unless you're in a hospital area that you have to create negative pressures in certain areas, it's a very bad thing because you'll hold your hand against outside outlets, you'll hold your hand against windowsills, and you'll feel the air being pulled into the environment. So again, negative pressures in a room is a really bad thing. Fire, situations. For example, if there's a house fire and there's smoke in a hallway, if you have a negative pressure in a bedroom, that smoke is being pulled into that bedroom. So our ideal conditions is either to have an equal pressure throughout all spaces in a building or a positive pressure. That's our goal. Return air ducts are best placed on the floor during heating season. Cold air falls. I want it to go in the return so it can be pulled in the furnace and heated up and blown back out through the house. In the cooling season, I want them near the ceiling. Okay, a lot of times in a very well thought out and constructed building process, you'll have 2 returns in every room. You'll have one near the floor, bottom side wall, and you'll have one near the ceiling. Okay, you switch them over. You close the one near the ceiling during heating season. The one on the floor is open. In the summer months, you close the levers on the one on the floor and you pull from the ceiling. But again, a lot of contractors don't do this because of cost. Okay, I'm talking ideal situations, but you're going to work for guys that don't do this because it costs more and the customer doesn't want to pay that cost. We want the returns furthest distance possible from the supply ducts. I want the air to circulate through the room before it gets sucked into the return. So when I replace a return duct, I want it as far as possible from the supply. Does that all make sense to everybody? Any questions on this? Okay. So when we talk about building ventilation, and this is extremely important because a lot of inspections, a lot of mechanical code, a lot of international mechanical code is built all surrounding proper ventilation these days. I believe everybody has probably heard the term sick building syndrome. Okay, sick building syndrome comes up when we have buildings that have notorious ventilation issues. People are getting sick, sharing germs, everything else. I mean, a perfect time for this conversation. But sick building syndrome means when germs are being spread, people are getting flus and everything else all the way across a building. Okay, the bottom line is that there isn't enough ventilation. Okay, ventilation ensures sufficient oxygen content. In other words, people aren't falling asleep at their desks. Air is kept at a reasonable temperature. We have a controlled fresh air intake. Okay, we have fresh air dampers. We have heat recovery ventilators. We'll talk more about those, HRVs. We have energy recovery ventilators, ERVs. Okay, we maintain a positive pressure on the indoor environment. If you walk into a building, okay, any building, any place, and you pull a door open, if that door opens and you can feel the air coming out of the building, just sort of like a slight breeze as you open that door, that building is being maintained in a positive pressure, okay, which means the outdoor contaminants are not going to be pulled into that building and all the exhaust is working properly. If you walk into a building and the air gets pulled in as you open that door, in other words, you feel it on the back of your neck where the air is being pulled into the building, that building is in a negative pressure. That means that we do not have proper insulation, ventilation in that building, and something is leaking air out of that building. Okay, 9 out of 10 times it's ductwork in the attics or basements. But again, we want to maintain all buildings in what we call a positive pressure. There's an ASHRAE standard 62-2010 which provides recommendations regarding ventilation. So basically, when you look at ASHRAE standards, the 4-digit number after it is the year that it was published. So this is now almost 20 or 10 years old where the newer standards have been published. So any system installed after 2010 from scratch should be the new standards. So this is a picture that was supplied by one of the ventilation companies out there. What we're doing is we have our air handler or furnace here. We have a filter that's in the center right under the word clean. So we're pulling fresh air into the return duct as needed. There's a little motor on top of that damper. We're mixing it with the return air coming back from the house, and we're pulling it into the furnace through a filter. We're either heating or cooling it depending on the time of year, and we're sending out a better a ventilated or purer form of air going out to the house. Okay, remember what I said yesterday. The solution to pollution is dilution. Okay, we're diluting our nasty return air with fresh air, and we're pushing it into the house. Now, what's going to happen is this house is going to be at a positive pressure. In other words, the pressure of the house is going to increase because I'm pulling air into the house using a blower. What that's going to do is all of my bathroom vents, my kitchen vents, are always going to be pushing a little bit of the dirty, stale air in the house out of the building. Even without running, you're going to have a little bit of leakage going out of the building. I'd rather have that than the little bit of leakage coming into the building. Because again, I'm controlling it. If I can control the airflow coming into the building, filtering it, cleaning it, and cooling it, I'm going to be in much better shape than if I don't control that airflow going into the building. So this diagram actually says a lot. Okay. The other issue we have with positive and negative air pressures all has to do with how you're pulling air in. The diagram on the left, okay, we have the building in a positive pressure. And again, we're going to talk more about pressures tomorrow. But if a building is in a positive pressure, that means the internal pressure of the building is over the pressure of the outdoor environment. Okay, so cracks and crevices along windows, I'm blowing air out of. Chimney, my air is coming out of it. Okay, in other words, it's going to go up out of the building the way it's supposed to do. If my building is in a negative pressure, in other words, my indoor environment is at a lower pressure than the outdoor environment, okay, I'm going to be pulling air in through my cracks and crevices. I have no control over the heating, cooling, or anything else of this air. That's where this becomes important. We resolve this with, this is a simple version, fresh air intakes. Okay, now fresh air intakes, when you're putting a fresh air intake into a building, there's two areas you never pull air from. Up near a parking lot or near a highway, because the air you're pulling in can be nastier than the air being pushed out. And if you're on a commercial building, you have to look at the roof layout. Okay, where are the bathroom exhaust vents compared to the fresh air intake? Where's the cooking exhaust vents if you're in a restaurant compared to the fresh air intake? Okay, because all of those things you don't want to pull in because of odors and other dangerous fumes that might be involved there. Okay, so again, fresh air intakes are very important, but they have to be placed properly. So there is a formula for required air exchange rates. Okay, now these formulas are rules of thumb. There's a true formula in the International Mechanical Code, which I think I show you in an upcoming day. We're going to go spend a little bit of time on that with regards to ventilation because this is so important. This is the key part of this term, okay, of this course. Required air exchange rate for most buildings, you take the number of occupants and multiply it by 15 CFM. In other words, I have to bring in 15 CFM of outdoor air per occupant in the building. Okay? That these days has actually even been applied to residential. New residential construction, I have to have these air exchange rates. How do we measure it? We do what's called a blower door test, okay? And we look for how much air can actually be pulled into the building. Okay, and I can actually get a true number. It can be based on building volume as well. In other words, how many cubic feet of air is in the building. and how much are we exchanging to the outside. But rule of thumb for ventilation, number of occupants times 15 CFM. So it's 15 cubic feet of outside air has to be coming into a building for every person that's average in the building. Okay, so time required for the air exchange, okay, is the size of the space by the air exchange rate. So if I have a 1,500, okay, cubic feet building, which is relatively small, and I have an air exchange rate of 15 CFM, okay, it's going to take 10 minutes to replace, 100 minutes to replace that, all the air in the building. So air exchange, total air exchange is the size of the space divided by the air exchange rate. Now, air exchange rate can be calculated or it can be measured. Air exchanges per hour. You take your time for one exchange and divide it into 60 minutes. You can figure out how many air exchanges you have per hour. Ventilation rates can be different for heating or cooling. Again, International Mechanical Code has tables that show you this, and we're going to talk about that. Okay, typical air exchanges per hour for residential. You want to exchange in heating times of the year, in heating season, we want to do a total air exchange of about 3 to 6 times per hour to keep a healthy building. In cooling, we increase that to 6 to 9 times an hour. The reason we have more in cooling is because we have higher humidities. There's too much that can happen in cooling. In office spaces, we want to exchange air outside 5 to 8 times an hour. Cooling, we want to exchange between 6 and 12 times an hour in office spaces. Public assemblies like theaters, town halls, sports arenas that are covered. We want to exchange in heating mode, which we rarely heat those. We want to exchange between 5 and 10 times an hour. A lot of times in these we use people as our heat source, okay? When it fills up, it gets warm. Most often we cool these. In cooling, we want to go 6 to 12 times an hour. Again, that's a lot of air exchange per hour. If I have that much air exchange per hour, what's the building owner's biggest concern? Why do we get pushbacks on this number of air exchanges? Anybody?
I would say because of cost.
Yeah, cost is a big thing. When I'm cooling and I'm having to bring in almost a 25% outside airflow, we're cooling a lot of extra air with sometimes very high humidity. It's very expensive. So a lot of times you're going to be asked as a technician to close down the outside air, okay, and cut off that outside air, especially if there's a landlord that's responsible for energy costs. Okay, the landlords are famous for this. They're looking for ways to cut money out of a building, and they're going to ask you to close down those outside vents. If you work for a good employer, or if you're self-employed as a contractor, okay, you need to be able to say no. International Mechanical Code sets these standards. I'm not allowed to change them. Okay, and if your employer says go ahead and cut down the outside air, ignore International Mechanical Code, you want to find a new employer because they don't care about you either. So, I mean, don't ever accept someone telling you to break the law in terms of code. There's reasons for this. In Pennsylvania, you don't have licensing on a technician level, with the exception of certain areas of the state. Okay, anybody who thinks they have the proper training can basically go out and become an HVAC technician. Okay, in a lot of states, we're licensed. Okay, and you're either licensed as a technician or a contractor. Once you hold a license in the trade, if you're taken to court over something that someone got sick or something like that, and you've made a change that goes against building code, you are personally liable because you have a license that says you know better. So it's very important that whenever you're asked to do something that goes against code, don't do it. I'm sorry, I can't do it. It goes against building code. Okay, you can show usually its national codes. Okay, so ASHRAE Standard 62 provides recommendations regarding ventilation. When you look in International Mechanical Code, they don't use the word recommendations. They use the word shall, S-H-A-L-L, which means you will. Okay, so there's a big difference. ASHRAE standards are recommendations, but all of the codes go back to ASHRAE standards. The standard provides basic equipment and system requirements and its minimum ventilation rates that should result in indoor air quality that's acceptable to human occupants. And again, this is so important because people get sick and people can have real issues based on indoor air quality, especially people with allergies, people with asthma, people with COPD. Okay, they have some serious issues the minute that air quality goes down. And it's surprisingly that the worst air quality you can find is in the assisted living facilities where a lot of our elderly end up. Okay, that is by far the worst air quality you will ever find, and that's because they're on a fixed budget there, and the owners of those buildings a lot of times start to cut down outside air. That's the first thing they cut down when they realize what their cooling costs are. So that's something always to keep an eye on. And again, I can tell when I open up the front door of a building that I'm in if they've cut down outside air, because the air is going to pull into the building behind me. If they have enough outside air, when I open that front door of the building to go do a service call, that air is going to push out at me. I can tell without even talking to anyone in the building, just by that, what's going on in the building. Attic and basement ventilation is extremely important. Okay, an unvented attic, it's closed off and it's essentially part of the conditioned space. Okay, so attics, if they're not vented, you consider them as part of the conditioned space. Okay, these three, this is very important when we're talking about load sizing. Now, as far as I know, every state in the country now is requiring vented attics for new construction. Okay, I think it's actually part of building code now. Vented attics, they use louvers or vents, soffit, ridge, gable. There's a long list. They use attic fans. They use ventilators. Okay, in my attic here, I have gable vents, I have soffit vents, and I also have a solar-driven attic vent that sits on the roof that pulls air out on the hotter days. Basements, okay, if they are vented continuously, they are not part of the conditioned space. Now, that brings some additional problems in as well. But if they're not vented, they are considered part of the conditioned space. We use exhaust fans, we use dehumidifiers, okay, for basement ventilation. But if they are not vented, they are part of your conditioned space. Conditioned space means areas we have to worry about when we're sizing our equipment. So, would crawl spaces be part of conditioned space? Anybody? Crawl spaces.
No.
Yeah, crawl spaces are not part of conditioned space, but they affect the heating and cooling of a house?
I don't think so.
Okay, if you have a crawl space that's vented properly, you can have cold floors if the insulation is not all that great. Okay, ductwork that runs through crawl spaces has to be very properly sealed. This is one of our biggest problems, okay, especially if you have an area of the country, if you're working in an area that has a lot of mobile home parks, or like the double wides or single trailers that sit up on blocks. Okay, the crawl spaces that are under those trailers, the ductwork runs underneath it a lot of times. The main ductwork, if it's not sealed, it's going to be sucking in all the contaminants under that trailer. Okay, and sometimes that's really nasty. Around here, I refuse to go under crawl spaces. I have some friends that actually live in some of these areas. Down here, they call them over 55 communities. Okay, I have friends who live in these areas, and I will not go and service their ductwork, even though they're friends, because I'm not going to crawl under into those crawl spaces. There's nasty things that live down there, snakes, alligators, and other such stuff. So, but crawl spaces, the ductwork has to be properly sealed. The insulation has to be good. It can really affect your indoor environment. Okay? During some seasons, under the right conditions, a whole house fan provides a building with free cooling. If you think about your area, okay, I call them the shoulder seasons. The early springs, mid-spring, late spring, where it's still cooler, and your house warms up, okay? We can actually use a whole house fan to blow out the hot air through the attic and draw the cool air in through cracked windows on the bottom floors of your house. Free cooling. Running a whole house fan instead of a blower and compressor is much more economical way of managing indoor temperatures. We do the same thing in commercial cooling. In a commercial building on a nice cool outside day, if the people load, the amount of heat generated inside the building by people and equipment, if it heats that building up over outside temperature, and I still have a nice, cool, non-humid day outside, I'm going to open up a whole bunch of dampers. I'm not going to run the compressor, and I'm going to pull in outside air into the ductwork, and I'm going to exhaust that hot air. Okay, it's part of the building control system. We use what's called an economizer, and you'll talk much more about that in the cooling or in your air conditioning term. But we use an economizer that basically allows me to pull in that cold outside or cooler outside air, and I basically just continue to do air exchanges throughout the entire building. Okay, I'm starting to see some of those on some homes as well. So if you have a system outside, if you have what we call a package unit, which houses all components in one, and if it has vent dampers, you can see them on the side of the unit that open and close. Okay, it means there's an economizer. We're pulling in outdoor air on these cooler days, and we're not running the compressor. The compressor is the key item of an air conditioning or heating system, okay, when we're talking heat pumps, that jacks up your power bills. Blowers are not that expensive to run. Ductwork delivers air to the conditioned space. Hey, we probably all know that. You have two ways of heating and cooling a space, through water or air. If you have pipes all over your house, you're heating with water, and you might not have ductwork unless you have air conditioning as well. Ducts deliver the air to the conditioned spaces. It moves air from a higher pressure area to a lower pressure area. My high pressure is the blower, the outlet of the blower. My low pressure area is the room that I'm moving air into. My duct pressures have to always be over that of the room that I'm pushing into. And we're going to talk about that because that's important if you don't have returns in every room. The duct characteristics, they're sheet metal or another non-combustible material. You are not allowed, per fire code, to run ductwork that is combustible. Because believe it or not, air ducts is the prime movement of smoke and fire when you have a fire in a building. Because they're wide open spaces that are designed to move air. Well, we can move smoke that easily. Ducts can be round, square, or rectangular. So we can have a round duct, we can have a square duct. Air moves in these ducts in different ways depending on the shape of the ductwork. We're going to talk more about that. There's a couple types of duct systems. This, again, if you grab the handout once I upload the handout, this is probably one you want to have handy because these ducts all operate in different ways. They have different efficiencies. Okay, we have a radial duct system. In other words, we come out of our furnace or air handler and we have one big plenum. A plenum is basically any place where all the ductwork comes together. We have one big plenum. We have a lot of flex ducts coming off of it. It looks like a giant spider web when you look at it. Okay? It's used frequently in cheap construction. It's a very cheap system to install. You can basically buy a whole bunch of flex duct from Home Depot, and a happy homeowner can go install their own duct system. or a company can contract out to a subcontractor where they don't have a lot of skilled technicians to run ductwork. Okay, very cheap system. Do not work as well as the higher end systems. Then we have what's called an extended plenum system. That's the bottom left-hand corner. You have your plenum in the center, but you'll notice the extension, the main ductwork on each side is the same size. It doesn't reduce. It stays the same size all the way down the length of the ductwork, both directions. Then we have takeoffs coming from these. Again, a slightly better system than the radial duct system, because now I have a plenum. I don't have a big spider web of ductwork. Okay, it's a little bit more organized, and the airflow is a little bit better. But again, we still have problems with extended plenum systems. The runs on the end are going to have airflow problems. Okay, so if this is going to a master bedroom on one side of the house, if this left top one is going to your master bedroom on one side of the house, and the one right next to the plenum on the left-hand side, that first outlet next to the plenum on the right-hand side or left-hand side, is going to a kid's bedroom in another portion of the house. Master bedroom has the thermostat usually right outside the door. Okay, that bedroom is going to be kept comfortable, but the child's bedroom that's closer to the plenum on the supply system is going to either boil or freeze depending on the time of the year. So extended plenum systems have some issues with controlling airflow and balancing everything out. By far the best plenum system, the best system installed, are using what we call a reducing trunk system. The further you get away from the air handler, the smaller the plenum gets. In other words, we have a big wide plenum as it comes, main ductwork as it comes off the plenum. The further away you get, the plenum or the ductwork reduces in size. That allows us to maintain pressure and velocity, so that the air coming out of the duct closest to the system is going to have the same air pressure as the duct coming away from the outside. Because as we take air away from a duct system, we have to reduce it in size in order to maintain that speed and the pressure that we need to remove the proper amount of air. So high-end installs use the reducing trunk system. Very important. The bottom right one is what's called a perimeter loop system. You put your furnace or air handler in the center, and then you feed a perimeter loop of ductwork. These are used in what we call a high-velocity system. Okay, there used to be a manufacturer out there called SpacePack. They had tiny little systems, and the ducts going out, these ducts were like vacuum cleaner hose size. Very small outlets. We could put them into houses, historical homes, because we could pull them through wall cavities without having to put it in big sheet metal or flex duct. Okay, so we used them a lot in the residential, architecturally designed, the homes that were built back in the 1800s, especially used to see these a lot in the Beacon Hill area of Boston, up near the gardens and everything, if you know about it. Used to see them a lot in Philadelphia, in the older neighborhoods where they had a lot of high-end homes that were historical in nature. We use them a lot in public libraries where we can't break open walls to install stuff. We can feed in ductwork of a small size. So the air handler is constantly pushing air into this perimeter loop system and keeping it pressurized. Any questions on the type of duct systems here or anything I said on this slide? Okay, moving on. Duct placement makes a big difference. I can place ductwork in basements, crawl spaces, attics. I could put them right into concrete slabs without basements. We put in the ductwork first, we lay it out, we pour concrete over it. Bad idea. 1970s construction, not done anymore. We can hide it in a false ceiling. Okay, if we take a look at the top over here, okay, the top right one, okay, we have our ceiling. we have a suspended ceiling. We use the entire space for supply plenum. Okay, not allowed anymore in code, but you will see it still in the houses that are out there. Okay, it uses a false ceiling. Okay, this one, the top one uses a false ceiling with diffusers. The middle one uses a false ceiling that has enough holes in it that the entire ceiling works as a register. You see this in older commercial buildings. So no matter where you're at in the building, you're getting fresh air holes down. Okay, in the bottom one, again, we use what's called a false ceiling with metal panels that allow air to come out. Again, you cannot anymore legally build new construction with false ceilings and what we call an open plenum system. Cannot use it. Okay, has to have supply ductwork now. It's illegal to do anything else. Duct construction is either made of galvanized sheet metal or other materials as permitted by local code. Okay, and I'll talk a little bit about the materials in a second. Joints and connections for sheet metal could be fabric, could be sheet metal, could be called starting collars or takeoffs. Ductwork has to be insulated. If cold air ductwork runs through a conditioned space and sometimes unconditioned space depending on where it's at, we have to insulate it. Okay, now according to International Mechanical Code and International Energy Code, we have to prove that the ductwork has been properly sealed and insulated. And we do that with what's called a duct blower test. We pressurize the ductwork and measure how much air we have to continue to put into the ductwork to maintain the pressure in the ductwork. Okay, some building codes do not approve of ducts made of aluminum, fiberglass, or plastic due to fire hazard. Many flexible ducts are made of wire and fabric that are also not permitted if fire could spread through them to other areas. You have to always check with the local building code. Local building officials, it's called the authorities having jurisdiction. That's a standard term in International Building Code. Authorities having jurisdiction, in other words, your building office, before installing ductwork. Once you're used to an area, it rarely changes, but you do have to check. Joints of sheet metal, okay, all come together. When you put two pieces of sheet metal together, and I'm not going to go heavily into this because this is actually covered in your trade skills course, which is where you do your OSHA 30 and we talk about ductwork. Okay, but sheet metal joints, these are all designed to hold the ductwork together, provide support, and prevent leakage. The most often you use is the drive clips. Then you can have different ones for different purposes. Okay, again, this is not something I'm going to really go over here, but I do want you to know that when you put sheet metal together, you have different ways of doing it. And again, it's all designed to prevent leakage. And then when you install sheet metal ductwork, wherever there's a joint together, we paint it with a sealer called mastic. It's a heavy, sort of a combination of, it's a cross between paint and plaster of Paris, I think is my best description to put it, okay? You paint it on there and basically seal the ductwork. Okay, very important. So then, the other way they do it, this is more often in commercial buildings, they rivet them together. You take two flat pieces of sheet metal, you put a rivet in. And again, you're going to do this in your design term, or I'm sorry, in your trade skills term. This is part of the trade skills course. Sheet metal tools, again, covered in a future course, but snips and seamers. Snips are one of the things you'll love to hate because you'll cut your fingers open if you don't use gloves because sheet metal is sharp. Snips a lot of times can give some really sharp corners. Seamers allow you to bend sheet metal in different directions so you can put things together. You can create different patterns on it, boxes and ductwork. We have two ways to insulate ductwork. Both of them have different values, insulation values, and purposes. Insulating ductwork on the inside is by far the most efficient from an energy standpoint of dealing with duct insulation. Okay? It also breaks sound. Okay, so if you have a louder blower motor, if you have louder rooms, if you have like in a commercial building, think about the school building. If we have a loud classroom and we don't want everybody else in the building to hear what's going on in that classroom, if we insulate the ductwork on the inside with foam insulation, okay, we actually prevent that sound from traveling. We can do the same thing on the square ductwork. So by far, the sound is one of the things with inside insulation. You have another way of insulating ductwork as well, and that's outside insulation. We put insulation around the outside, and that's what we see on flex duct. The picture on the right is flex duct. Okay, we have insulation around an inner it's a metal and plastic component. It's sort of like a slinky. You stretch it out. There's plastic between the different areas of metal or wire that's in there. Over that, we put insulation. So this is insulated on the outside. And then there's outer metal jacket that's designed to protect this insulation and protect the ductwork. This is flex duct. Now, when you look at this, there's ridges in here. Okay? These ridges collapse and become more pronounced if the flex duct isn't stretched all the way. So when you put flex duct in, you have to stretch that ductwork. You can't just have it in one lump. You can't just take it out of the box, not stretch it out, and connect each end, because your airflow will go downhill. The more ridges we have in ductwork, the less smooth ductwork is, the lower the airflow is going to be, because there's resistance to airflow here. Non-metal ductwork is made of fiberglass, urethane, plastic, sheetrock. I don't see that often anymore, or some textile ductwork. Textile ductwork used in sporting arenas quite a lot, because you can make it appear to be whatever you want it to be. It's used by architects when they need to get ductwork and registers into certain locations, but you don't want to have a lot of heavy ductwork hanging in the ceiling. You want it to look nice. That's when they use textile ductwork. Plastic ductwork, we basically use a lot of times if it's harsh environments. Urethane, I don't see used all that much. Fiberglass, we'll talk about that when we talk about duct board on the next slide. Okay, duct board is probably the nastiest stuff you have to work with in terms of duct work. What it is, it's pressed fiberglass between an outer sort of foil layer and an inner layer of insulation. You cut these. You cut the inside, leaving the outside intact. You can almost see it on that right picture. And you can actually fold this in different patterns and make duct work out of it. It's insulated. It's actually pretty energy efficient, but it has a lifespan of about 10 years. Because what happens is this inner layer, the dark layer on the top of the left-hand picture, starts breaking down over time. As you blow hot air across it, then you blow cool air across it, then you blow hot air across it. It breaks down over time with those temperature changes. And what that leaves exposed is the compressed fiberglass on the inside. Well, compressed fiberglass in an indoor environment is a problem because you're blowing those particles of fiberglass around the airstream. People don't realize how bad ductwork that's disintegrating can be. Down in Florida here, and once you get south of Georgia, this is all you see. Georgia and south, it's all you see. Around the mid-southwest, this is all you see. It's duct board. Okay, cheap install, because you can basically construct your ductwork on site. You don't need a sheet metal shop. You don't need specialized people to do sheet metal. Okay, you can avoid the sheet metal union that controls a lot of the area with ductwork. So you can install duct board for very inexpensive installs. So 2 guys working out of the back of a pickup truck can duct an entire house probably in a day. These guys are fast with the stuff. But it doesn't stand up to weather. It doesn't stand up to use. And then somebody will decide to have their ductwork cleaned. The brushes they use to clean ductwork will rip this inside layer apart. So now you have clean ductwork spraying fiberglass all over the place. Okay, so again, just be aware that there's ductboard out there. Oh, by the way, never step on this if this is in an attic. It cannot support your weight. Okay, be careful working around the stuff because it will break down, and if you step on it, you own it. Any questions on the different types of ductwork? Okay, I'm assuming that there's no questions because I'm not hearing anybody. So, moving on. Duct material cannot release any loose material into the airstream. Again, see my notes on the fiberglass ductwork. Ducts made of asbestos. Well, I don't even want to see asbestos in ductwork anymore. This is old. But fiberglass should be plastic coated. Remember, asbestos is fine as long as you don't disturb it. Okay, so the minute you start replacing pieces of ductwork that are made of asbestos, it becomes an environmental cleanup. So if you have asbestos ductwork, if somebody cleans the ductwork with a brush, all of a sudden you have an asbestos problem. Asbestos ducts must be replaced when installing a new furnace. If the furnace is not being replaced, the ducts can be sealed. Again, asbestos ductwork, the best thing you can do for any customer is to replace those things. It's a bad idea. Duct dimensions, the size transitions should be tapered. Okay, in other words, we reduce transitions 1 inch for every 4 inch in length, and we're going to go through that as we start talking more about ductwork design. So don't worry about these numbers for right now. As you reduce ductwork, we don't do it suddenly, we do it gradually. As we enlarge ductwork, in other words, we go from a smaller piece of duct to a larger piece of duct. Again, we do it gradually. Okay, the aspect ratio of length to width to narrow side. Okay, a ratio of 1 to 1. In other words, if we can have square ductwork rather than rectangular ductwork, it maximizes capacity and minimizes material. That isn't always possible because of where you have to put it. You have to allow space for fittings and clearances. New construction, one of the biggest problems that I've seen in new construction is they put the air handlers and ductwork in the attics before they put the ceilings in. Okay, so your company goes out and places the air handler, puts the ductwork in, and then the contractor comes back, the sheetrock contractor comes and puts the ceilings in. Okay, then they put the attic access in, usually pull down stairs or an attic hatch. You might have your air handler in a space in that attic that doesn't have any more access. In other words, you can't fit over the ductwork to get to the air handler because you were trying to be the nice guy and put your air handler off to one side that allows them to use the attic for insulation and storage. Okay, so reading blueprints becomes very, very important in new construction because you have to know what the finished product is going to look like. Because if you have an air handler blocked in a corner of the attic with ductwork and everything else, your service techs are going to hate you. Okay, you have to allow space for service. Okay, I'm going to basically skip over this table here because it really, again, we're going to talk more about this when we talk about blueprints. This is a duct aspect ratio table. Registers, diffusers, and grills. Okay, how these are designed is extremely important. Registers deliver air to the room. Adjustable directions are on the registers. In other words, if you look at the picture on the right, how my register is installed makes a difference. The circular registers have will put air in all directions, as well as the square one. The ones that are not circular, that have like only the two, like the left-hand one, the entire left-hand one, will throw the air in two directions. Okay? Just a couple more slides and then we're going to stop for the day, but I want to get through a couple more things. The diffusers, they're non-adjustable supply fixtures. The one on the right-hand side of this picture, it's a diffuser. spreads air more uniformly than registers. Grills are non-adjustable fixtures covering return ducts. So again, registers and diffusers are on supply ducts. Grills on return ducts. Any registers with ductwork that passes from an unconditioned space into the conditioned space needs to be sealed to the drywall. So if you have a ceiling register that's coming from an attic, it's required by law to be sealed, okay, so that air can't seep around it. It reduces heat leakage and improves energy system efficiency. Dampers control airflow in forced air systems. It allows you to stop or start airflow, and it allows you to balance airflow. So as we pull a duct off of a main piece of ductwork, we have a damper in there that allows us to control how much air is being pulled out of the ductwork into my branch duct. Okay, you have different types of dampers: butterfly damper, multi-blade damper, and split damper. In residential, you're going to most often see the butterfly damper. That's the top one. In commercial, we start getting down to the multi-blade dampers. Okay, we use them all over the place for airflow control. Split dampers are used as fire dampers. We're going to talk about that as we start talking about some of our blueprints. Most dampers have automatic controls. They open or close based on the thermostat signal. Okay, we have power devices for dampers that could be electrical motors, pneumatic systems, hydraulics, and solenoids. We also use variable air volume dampers. In other words, we keep the temperature in the main ductwork standard, but we control the temperature in the room by changing the amount of air that's being allowed into the room. That's called VAV systems. You use them in heavy commercial, office, and big building environments, VAV. No thermostats around the spaces. We maintain the temperature by sensing the return air temperature from the building overall, and we allow different quantities of air to come into the space and that's how we control the internal temperatures. We're required to have fire dampers. I've mentioned this a few times. They close automatically on the detection of heat. Anytime you have a firewall with ductwork going through the firewall, and again, we're going to see this on blueprints, you have to have fire dampers. You have static fire dampers. You have dynamic fire dampers. And we have different ratings of them, Class A, Class B, and Class C, depending on our environment. How do you find out where you need fire dampers? Check with your local code authority. Okay, make sure any fire and smoke dampers are installed. Install dampers in strict adherence to manufacturer's instructions. Fire and smoke dampers are not something to mess around with. They can cause real problems for the fire department if there's a fire in a building. So that is where we are going to stop today. If somebody wants to remember or remind me if I forget in the morning, we're stopping on slide 40. I think I've hopefully talked long enough today to get us started. There's about 17 more slides in this presentation, and then we're going to move on to pressures. Does anybody have any questions on what we've gone over today? You guys can wake up now.
I got a question. The heat pump doesn't work the same thing of the air conditioner, right?
Say that again, I'm sorry?
The heat pump, it doesn't work the same as the air conditioner, or yeah?
It's the same principle, but we're changing the direction in the way we move the heat. So in other words, in a standard air conditioner, I have a condenser outside and I have an evaporator inside. In a heat pump, I just changed that around. My condenser, which is blowing off the hot air, goes inside, and the evaporator that's absorbing heat goes outside. So we're just changing the direction of the heat movement.
Okay.
Actually, the heat pump in most parts of the country, as long as you have temperatures average above 32 degrees, your heat pump is by far the most efficient type of heating and cooling system you can have.
Yeah, I got one, so, I have to do some, fix here.
Yeah, what you can do is, I mean, basically what you look at when you're looking at a heat pump, if it's in heating mode, your outside unit is blowing cold air out of the top, and the large line coming out of the outside unit is hot, the suction line. In the cooling mode, the large line gets cold, and you're blowing hot air out of the top of the outside unit. That's the easiest way to tell if the reversing procedure is working properly.
Okay, thanks.
Okay, any other questions? Folks, I can't say it enough. Please participate in the discussion boards. Please watch the due dates on the assignments. I try to be a little bit forgiving about it, but there comes the point where a lot of people start missing due dates. A lot of people don't participate in discussion boards. I become less forgiving. Today, the discussion board you had yesterday on psychrometrics was awesome. Okay, thank you guys for commenting on other people's posts. I saw some corrections being done in there for people's posts, and that's the type of discussion we want to have. So there is a discussion board out there today on air distribution. You can look at the houses you're in now. You can look at your own house. You can look at other buildings, and you can use examples that you're seeing. And if you tie it back to an example, it's probably the best way to deal with those discussion boards. So don't forget about the labs. Don't forget about due dates. Very important. And I will talk to you all tomorrow when we're going to talk about pressures. You guys have a great rest of the day, and thank you much.
All right, you too.